before already. The main thing I want to reinforce is that OpAmp does not do anything special to you. It just provides you an extra equation, right? If you insert the OpAmp into your circuit, in addition to KCL, KVL. And what are the equations? You can have two, right? We say the V out equals to A0 times V plus minus V minus. That's what an OpAmp does, right? It amplifies the difference between these two inputs. But when do we use this equation? Just for the sake of solving a circuit. Great. Someone say long ideal, but still some people may argue with you. Depends on your definition. But the main point is A0 is finite. Then we use this one, right? But if we're so lucky, the A0 is infinity. What will we do? Yes, we will just assume for our class V plus equal to V minus, which we call it virtual short. But we always need to warn ourselves. This is just a class exercise. You trust me. I give you something that you can use virtual short. But when you design your circuit, you go taking the circuit design from other people, you need to make sure that you have a large gain and also you have some proper feedback, right? If you don't have the proper feedback, you cannot assume it is in virtual short. Okay, for example, here, I give you this circuit and you can assume it has a proper feedback. Of course, you need to check it later in principle, right? But you can trust me, I'm not going to trick you. But when you're doing your real design, you need to be careful. It has this proper feedback. When the gain is infinity, the V out is going to change such that it's going to force this point to be the same, almost the same as this point. And that's why you can assume V plus equal to V minus. Okay, so remember these two equations, right? So I answered this already. Now, so in principle, if you have time, you just sit down, be careful, you can solve any OpAmp equation you want. Just like adding one more equation to the circuits, right? But what if our circuits contain some capacitors and inductors instead of just resistor, right? What should we do? Well, I think you also know how to do it, just do integration, differentiation. But there is a better way, right? Which we can consider to use the frequency domain to play with this. So let's see what it means, right? So first of all, if we work in the frequency domain, what is the impedance of a capacitor and the inductor? How about for capacitor? What is the impedance? Thank you. 1 over SC, right? Sometimes we may just write 1 over J omega C, okay? So this is the impedance in the frequency domain. Okay, we will discuss a little bit more. Then how about the impedance of the inductor? SL, thank you. Right, so I hope everyone can say this as fast as these few students, right? This is something you really need to know as an electrical engineer. Okay. SL is J omega L, right? We ignore the real part, which is okay. Now, if I write everything in the frequency domain, and actually something very trivial, how about the impedance of a resistor? Just R, right? Now, then, how does the Ohm's law change, right? We know Ohm's law is what? V equal, it's different, thank you. It's like, maybe just like V equal to IR, right? We know this very well. The potential drop across the resistor is equal to the current times the resistance, right? So similarly, if we go to the frequency domain, you can say V of S, right? Just say of S because I want to say it is in the frequency domain. I just remind myself it is in the frequency domain. Equals to the current in the frequency domain times the impedance. That's it, right? So this is still the Ohm's law. It has exactly the same form. If it is a capacitor, I put in ZC, 1 over SC. If it is an inductor, I put in SL or J omega L, right? If it is a resistor, I just put in R. Okay? So if I say this, then let's review. Let's think about what we did last week. We tried to derive all the equations using KCL, KVL, and the OpAmp equation. And in this process, we also use the Ohm's law. We wrote it as V equal to IR. Now, if I work in the frequency domain, KCL, KVL are still the same, right? The OpAmp equation are still the same, right? For example, virtual short is still virtual short. At different frequency, they still virtual short, right? Or for this gain, yeah, I need to make the gain to be frequency dependent, but the form is still the same. Output equal to the gain times the difference of the input. So everything is the same. If I ask you to rederive all the equation we studied last week, last class, you should get exactly the same results, right? The only difference is just that you need to put a parenthesis S, if you want to be specific, in all this quantity to say that they are in frequency domain. So this is the thing I want you to agree, is that if last week I derived the gain of this inverting amplifier as negative R1 divided by R2. Now, if I try to do it again today, but I use frequency domain, I should get the same form, exactly the same form, because the Ohm's law has the same form. The KCL, KVL, and OpAmp has the same form, right? So I will get this equation, except that maybe I want to be a little bit more careful. I would say V out in the frequency domain divided by V in the frequency domain equals to the effective impedance of this one divided by C2, right? And if this is resistor, I just substitute as R1, R2. If this is capacitor, I substitute as 1 over SC. Or if it's inductor, SL. Right, so I spent time to talk about this. I hope you will be confident in doing that, right? You know why we do that. We prove it, right? So it would be good just quickly to remind ourselves again, what is the meaning of time domain versus frequency domain? It's actually nothing special, maybe too trivial for many of you. But let's, for example, think about a wave, a signal in the time domain, right? So this is the voltage, and this is the time, and we say this is the V of t, because, right, we're talking about the voltage at different time. And now I put this here. And this is a cosine wave, right? You trust me? And for example, I can say this point equal to 0. This as not 0, this equal to 1, right? 1 volt, for example, right? And then how about I say this one is at, let me do more, right? This is the whole cycle, right? So this is 1 second. This is 0.5 second. Is that okay? Just any signal, right? This is an example. So we will say, okay, what is V at 0 at t equal to 0? Is equal to 1 volt, right? Thank you, right? V at t equal to 0.5 volts equal to negative 1 volt, right? And then V at 1 second sorry, I have many typo here, equals to 1 volt again, right? That's the period. So every signal, right? This is a simple cosine wave. It is like this, but you can have any signal, like what I'm talking about. When I'm speaking, you go to the, I make it in microphone, you get the electrical signal. Then you can say at time equal what, at 0.5, what is the magnitude, right? Or even you can include the phase or whatever, right? So this is time domain, right? We can also say, I'm going to describe this whole thing in the frequency domain. What does it mean? We then say, hey, this signal, it can have different components. I will just call this frequency, right? And now the unit is hertz instead of second. Basically, we also talk about the voltage. But if we look at the frequency domain, you have learned about Fourier transformation, Laplace transformation, right? You basically get something like this. This is 1 hertz, right? Maybe this is like half, negative half, for example, right? No, don't worry if you forgot about that. I don't need you to do Fourier transformation or Laplace transformation in this class, right? You can always Google. If you know that, you need to do that. Wikipedia is so easy, a very nice table. But the point I want to tell you is that this whole signal, right? We live in the time domain. I will feel comfortable to say at this second I have this voltage. But the nature does not revolve around the human being, right? We can describe the nature in a way that we are not comfortable with, but mathematically very simple. It's in the frequency domain. We say, hey, this signal has a component at 1 hertz. Because indeed, if you tell me that you have a signal that is cosine wave and it is 1 hertz, I can reproduce the whole signal already, right? You don't need to tell me that at 0 it is 1, 0.001 is 0.9, 0.00, 0.2 it is what? In order to reconstruct the signal, you just tell me I have a cosine wave with 1 hertz. Then I can construct the signal that contains all the information. So that is another way to describe this signal. And then we can, in this particular case, we will say, for example, okay, what is the V at 0 hertz? 0. You tell me no DC signal. When I'm talking, there's no DC signal coming out, for example, right? And then we say, okay, F equal to 1 hertz, right? It is, there is a delta function. We are going to be lousy. We just say, okay, 1/2, for example, right? So, of course, if you have a complicated signal, you can have a complicated frequency domain, but doesn't matter. You just tell us you have that much components of that frequency, right? So that is what we mean by this frequency domain. So when we are playing with this voltage V of S, instead of talking about V of T, we're talking about, you tell me what frequency you want, I tell you what is the components for that frequency. Okay, make sense? So this is just a review. And then what is that? Now, if I have a time domain signal V of T, like this one, right? It keeps changing. This is a simple one. Again, it can be a complicated one like my voice in the microphone. I can transform it through the so-called Laplace transformation and go into the frequency domain, right? Maybe like this, okay? So do you need to memorize this? No, not even put in cheat sheet for this class. But why I want to do this, because we are going to use the equation to help us to solve the OpAmp. So if you have signal in the time domain, you use Laplace transformation, you bring it into the frequency domain. And just to remind you, the frequency domain is not just omega, it's sigma plus j omega. But in our class, we can just think of omega. And you can do the inverse transformation also, right? Why this is great. If you have a differentiation in the time domain, if you do a transformation, it becomes just a multiplication in the frequency domain. If you have an integration in the time domain, it becomes a division in the frequency domain. So one good thing about Laplace transformation is that it converts your differential equation, right? That's very scary, differential equation, to just a simple algebraic equation. You only need to deal with multiplication and division. So I like to use this as an example. It's like someone give you a test paper, maybe a elementary school math test paper in Russian. You don't know Russian, looks everything is so difficult. Like let's say they don't write in Arabic, just everything in Russian. What do? You translate to English. Then you do it so easy. Oh, it's asking what's 3 plus 4. When you're done, you translate back to Russian, right? So you let Laplace transformation to do this translation for you. And then you do the math all in English, for example. Okay? So what do you need to memorize? The important thing is to understand that we have time domain and frequency domain. This can be used as a tool to help you simplify the task. You don't need to memorize this equation in your exam, but you need to know that we have this thing because you use a lot in engineering, right? You can Google, Wikipedia to get all this equation. So now we are going to use this to help us to solve the circuit. But before that, I want to emphasize one more time what we are doing in the frequency domain. In the frequency domain, as I just said, we're talking about the voltage as a function of S, let's say as a function of the frequency. And we talk about something called transfer function, but that's nothing special. It basically is talking about output divided by input, which can be just the gain, right? Output divided by input is the gain. But it can be many more. It can be different type of gain, but we just call it transfer function. Whatever you put into the system or circuit, you get something out, right? So what is the relationship between output divided by input? That is the transfer function. And we put it in the frequency domain. Now, because it's output divided by input, we usually can factorize it into a polynomial, right? It usually is represented in a polynomial. Polynomial is like what? an Sn plus an minus 1 Sn minus 1, right? All the way to a0, a polynomial, right? And they have roots, right? And I can factorize it into two forms, okay? And those roots that make them become 0, right? The roots means you substitute s by those number, then the whole term will become 0. For those on the top, we call it zeros. For those at the bottom, we call it poles. Okay. Now, if this is a little bit confusing, you need to go back to think a little bit more. But you trust me now, every transfer function, right, in our class is just a ratio between a polynomial and another polynomial. So how do I find the poles? I will set the denominator to 0 and then find out what make it 0, right? For example, here, I have a transfer function. This is a simple transfer function. Again, it's in the frequency domain. V out of S divided by V in of S. When you see this, again, remind yourself, oh, you're talking about when S is 1 Hertz, right? V out at 1 Hertz divided by V in at 1 Hertz. What it is equal to 1 over 1 plus 1 Hertz times R1C1. That is the meaning of this equation, right? And we want to find out the poles and zeros. What is the 0 in this case by definition? Very good. You need to follow the definition for zeros. We need to set 1 equal to 0, right? Because the denominator is 0. It is 1, right? Is it possible? We say impossible, right? It's just saying that I cannot find any s so that 1 equal to 0. So we say there's no 0 in this system. How about poles? What do I need to do? Yeah, you gave the answer already, but we'll do 1 plus SR1 C1 equals to 0. And then you get, okay, I do have a pole, which is P1 equals to negative 1 over R1 C1. Okay, so that is a pole, right? So let's do something similar for this one. On the right, right? Do we have a 0? Again, no, right? Because you cannot find any S so that 1 equal to 0, right? 1 never equals to 0. How about for pole? What do we do? You need to set it, okay? So it's very tempting to just jump into a conclusion. Now, when you set it, you see that S equal to 0. So it has a pole at 0 frequency, okay? Not 0, right? It's confusing, right? So 0 is just a name saying that those frequency make the denominator equal to 0, or they're the root of the denominator. Okay? Okay, this is transfer function, right? So you know that already, just a quick review. Now, then we want to solve this circuit. This is called integrator.